Okay, logs day 1. By the end of the hour, we want to make sure you understand what the heck a logarithm is and why we need them. Because they're there for a reason. If we didn't need logs, we wouldn't make up a whole new system for doing math. But we need them. And also, this is not on the list here, but I want to show you a few things in the real world that we use logs to do. And you're going to do some basic evaluating of logs, like you'll be able to look at a log problem by the end of the hour, and even without a calculator, you'll be able to do this weird math. It's kind of like an equation. It's a log. All right, logs are used whenever you have a big range that needs to be narrowed down to a simple scale of like 10 to 12 to 14 numbers. What I'm trying to say here is, like, for example, decibels. Do you get how there's not, like, noises that are so quiet that you can barely hear them? I mean, we're just barely hear it. Yes, like the mosquito that's just far enough away that you can barely hear it buzzing. All the way to, this is kind of a cool concept, a noise that is so loud that if you hear it once, you'll never hear again. Isn't that a weird concept? There are noises that are so loud they will destroy your hearing. So obviously there's a lot of noises kind of in between where they're loud, but they are not so loud you go deaf immediately. But there are some that could destroy your hearing immediately. Anyway, there's a huge range, and you can simplify decibels down to a very small number of numbers. I'll give you another example here. The pH scale. There's a huge range of how acid something can be. It can be as acidic as pop, which is actually fairly acidic, and all the way up to, by the way, just to clarify, all the way down to, this is the lowest. It's 0, and that's battery acid. Actually, battery acid is here. Okay, and this is more like dangerous than battery acid. First of all, to get battery acid on your fingers, it would burn. It would hurt bad. But there's like acids that are way worse. Like you put a drop on your hand, it'll burn right through. Okay, it's that acidic. It's that awful. So battery acid's here, and the super bad acids are here. And you might say, well, then they're pretty close to each other. Actually, each of these is 10 times more acidic than the other. Each of these levels gets 10 times more acidity. Okay, so to go from lemon juice to battery acid, you might be thinking that's, so you're saying lemon juice, that's not that scary. 10 times. That's what logs do, is they can let you have a base of 10, for example, and then that means every time you move one number, you're moving 10 times as big. Yes, sir? What that means is fish that are like full-sized fish, like fairly healthy, big fish, can't handle it this acidic. So in other words, if you're in that zone right before vinegar, then it's acidy enough. Have you heard of acid rain? Acid rain comes from the clouds. Basically, if there's too much nasty chemicals in the clouds, when it rains, it comes down kind of acidy water, and that can get in the lakes and can kill the fish. Well, baby fish are very sensitive. They would die with just a little bit of acid, but even adult fish die at this level. Okay, so the point is that, again, between milk and, milk and water, milk is 10 times more acidy than water. Keep moving it this way. Vinegar to lemon juice is 10 times more acidic than vinegar. All right, so these are steps of times 10. Same thing happens on the Richter scale when you are talking about earthquakes. We don't have them around here, although we could. Did you know that we're actually on an ancient fault line for earthquakes? Now, that just means there hasn't been one since anybody can ever remember. But there is, in this area, it is possible we could have an earthquake. It would just be something that happens every maybe 10,000 years or something, but stuff like that happens sometimes. All right, so on the Richter scale, you might think this was a scale 3 earthquake compared to a scale 4. Well, they're pretty much the same thing. Nope, 10 times. So a scale 4 is 10 times as big as a scale 2. Just for perspective, you could feel a level 2 Richter scale you could feel something happened. Like, ooh, I just felt something. Just barely, though. Okay, all the way up to 10 times bigger than that would be a 3. 10 times bigger than that would be a 4. 10 times bigger than that would be a 5. Get what I'm saying? So it's every time you step up a notch, it's 10 times bigger. So when they had that one that caused the tsunami in Japan, that was a 9. And that you could imagine how insane the shaking would be if you were at the epicenter, which is like the main place where the earthquake's happening. Now, what's a 10? Nobody knows. Nobody's ever seen a 10. Okay, and it would be 10 times as big as the biggest earthquakes that we've ever seen. Okay, and obviously 10 times as big means that the ground goes up and down 10 times as much. Okay, so it'll knock you off your feet on a 9 if you were in the area. And again, earthquakes don't just kill you because they shake you up and down. I mean, that doesn't really kill you. It's the fact that buildings fall on top of you usually. That's the problem. So if you were out on this street, for instance, when the earthquake happened, yeah, it'd be really scary, but you wouldn't have died. You'd have been fine. If you were in a big building that then collapsed because of the earthquake, that's what causes the problem. So the new systems that they have in California to try to prevent earthquakes, their buildings are built on rollers so that they can wiggle back and forth. You'd never see it. It's not like on the street level. It's down in the basement where you wouldn't be able to go. But they have these roller systems so that the buildings can move several inches, probably even feet on the really big buildings. They can wiggle back and forth because that allows it to take out that stress of the shaking, and it can just like move side to side and be okay. If you have something that's really rigid like concrete, just pure concrete all the way into the ground and across the floor, then when things shake back and forth, it just cracks and then becomes unstable and can just collapse. So point is, if you've got newer technology, you probably could survive a 9, but they aren't built to handle a 10. So again, there's so much raw power in the earth that we can't like even fathom it, that you could have an earthquake that's so big that even with the best technology, your building is going to fall over. All right, so let's talk about why we need these things. That one on the end there, that's the only one you shouldn't be able to solve. Solve the 3 on the left. Should be easy peasy. And then if you want to use the calculator, you can play with the calculator to try to figure out the one on the right. And you might get close, but if you knew how to use logs, you could do the one on the right. Let's see how close somebody can get. If you haven't already, borrow a calculator. I have more if you need one of mine. Just have to come up and ask. Mm-hmm. And yeah, you can even guess and check on that last one. It'll eventually you'll find you get close. Like 2 to the power of 2 would make 4, so obviously it has to be bigger than that. So it must be 2 point something. 2 to the power of 3 would give you 8, and that's too big. So it must be 2 to the 2 point something. You know what I'm saying? Yes. Oh, I get what you're saying. You're saying in the old days, like last unit, this would have been an 8, and then you would have said, yeah, 2 to the x equals 2 to the 3rd. You're right. We can't get the same base with a 7 like that. 7 can't be made up of a 2 to the something. If it was, then we'd know the answer already. See, 2 to the something. So you're right. You can't solve it by making the same bases the same. This is the generic way of saying that we need this to be 2 to the something, but it isn't. And so, all right, so logs will help you solve that, and I'll show you in a minute how that works. Did anybody get close? What was it, like what'd you get? 2.107? You think you're closer? 2.8? 2.809. Okay. Well, how do I know? Well, I'm just going to put it in the calculator. I'm off to the side. It's not on the screen. Sorry, folks at home, but I'm going to go 2 to the power of with a little caret thingy. 2. I'm hearing a lot of people say that 2.8 worked. 2.8009 or whatever. That's 7.007. So it's really close. This one's really close. I think you're just off a little bit. Did you try it? Like, did you double check it? 2 to the 2.1. I'm just try it. 2 to the 2.107. I think you messed something up there because 2.107 didn't work. But thank you for trying. Okay, so 2.8-ish. How do we get the exact answer? You use logs. We had a way to get this x alone. We minus 2 from both sides. We had a way to get this x alone. We divide by 2 on both sides. A way to get this x alone. We square root both sides. And by the way, did you remember it was plus and minus the square root of 7? I think a lot of you probably forgot that. It happens over and over, and people keep forgetting, and it's normal. You're forgetting a solution. It's called dropping a solution. Because 2 things work in here, not just square root of 7, but also negative square root of 7. Okay, over to here. 2 to the what is 7? We figured it out. X is about 2.801 or whatever. Then, how did we get that? What did we do to both sides? What we did is rewrote it as a log. And I'll tell you what it is, and you won't understand it yet, but log base 2 of 7 is what x is. And then your calculator can do that log base 2 of 7. And it would be actually typed in a different way than you'd think. You'd have to type in log 7 over log 2. You'll learn all that later, but the point is you can use these logs to get x alone. All right, over here, this is just a reminder of what Jack was saying. That can't you just make the bases the same? Yeah, if we pick certain convenient, nice numbers, yeah, we can make the bases the same. But what if you can't? Like here, the 2 and the 7, they don't have the same base. And the 4 and the 9, they don't have the same base. So we need an inverse operation that undoes a variable exponent. And that's what logs are. Logs are kind of like the arch nemesis, like divide and multiply. Superman and Lex Luthor. Exponents and logs, they undo each other. Okay, so here's some examples of changing a normal problem you can relate to. 3 squared is 9, right? In log world, this would be said log base 3 of 9 is 2. This is the base. This is the next number we come to. And then you jump back over here. So it goes in this little circular sort of a motion. Log base 3 of 9 is 2. All right. I know you don't get that yet, and that's okay. This one. So when I started with saying this is an example of why we'd need logs. It's log. Now let's just think about why would this little subscript number, this little number on the bottom, be a base? Because this is the base and that's the exponent, right? So the base number of the log is 2. And then it would be wonderful if it was just in order, 2 and then x and then 7, but it's not. So then you just got to remember that you have to jump around. I'm very tempted to play that song. Okay, so 2 goes over to 7, so that's next. Equals, come back to the x. X. Log base 2 of 7 is x. Okay. All it is we were rewriting an exponent problem into log form. Now these logs are nothing really special. They're just like ratios. And you could, in fact, when they first figured out logs, there weren't computers. And so all they did was they made a list of these ratios, these decimals. Because remember, the answer for that one that we've just got up on the board there is 2.810 or whatever. 2.8 2.8107. Get it closer? 2.807? Okay. So if the answer is 2.807, you would have just looked it up on a chart. There's charts for this. Then after that, they moved to the slide rule. Slide rule is this plastic thing that you slide this piece in and out on, and you line up certain numbers on it, and it could tell you the answer. And of course, now we've moved to the digital age, so we use a calculator to get us these decimals. But basically, you just look it up on your calculator once you got it to here. I'm sure you can probably Google something like this too. Just like you can say, what's the temperature in Frankfurt right now? You can probably ask Google, what is log base 2 of 7? And it'll probably just tell you the answer. It's just like asking it, what's 2 times 7? You can Google that. So, all right. So, let's look at how we set these things up and what the terminology is. This comes from this. Do you get how it's always exponents and logs, and they're like kind of related? They're like undo each other, just like, what's another example of a superhero who has a nemesis? Batman has had several nemesises, though. Is it would probably nemesi then? I don't know. Nemesis? Probably nemesis. Anyway. Joker and, you know, the other bad guys. Okay. What was that one that was Mr. Freeze or something? Yep. Anyway. Okay. So we have the base is this little part. That's called the argument. We can argue about why it's called the argument, but it would be kind of a circular argument. Okay, anyway, and saying it is important. Log to the base b of x equals y. I'm gonna write you one. Now, some people say to the. I think it makes it more cluttered. I think we should just throw in these, red words, and you'd have it good enough. Log base 3 of x equals 10. Or you could say log base 3 of x is 10. Sometimes we can change is and is equals 2 is the same thing pretty much, isn't it? 2 plus 2 is 4. It's like 2 plus 2 equals 4. Is and equals are pretty much synonymous. All right, so log base 3 of x is 10. So the problem is kids have this on their paper and they really, unless I talk it through, they really don't know how to say that. I'm going to say y this time, just to show you it doesn't always have to be an x. So, how do you say that? Say it one more time, a little louder into the microphone. Go ahead.
Log base 8 of 2 equals y?
Yes, perfect. Nice job. So all I had to do is throw in the word base and this word of. Okay, good. So I want you all to say this one in a moment with me. Ready? Log base 12 of x is 10 or equals 10. Either way. Okay? I just need you to know how to say it, because you seem really silly if you can't say the problem to the teacher or to the kid next to you. If you can't even say the problem, you know what I mean? Okay. So then what does this really mean? This is a log problem that has an arch nemesis, which is the exponent version. But sometimes the log version is better than the exponent version. One of the two versions will give it to you in a form where x is able to be alone. If we want to get x alone here, we just have to rewrite this puppy. This could have been an exponent problem of 12 being the base. Which of them is the exponent, the 10 or the x? The 10. Remember how you have to go back and forth? You jump over to this side to get your next number. 12 to the 10th is, come back to this, x. That's the exponent version of it. Do you get, in this case, the exponent version is better because x is alone? This one doesn't tell you the answer. This one does tell you the answer because x is alone. It's 12 to the 10th power. It's a huge number. You use a calculator to find it, but you can find x now. All right, how about this one? 5 to the x equals 8. Is it solved right now? No. So you have to rewrite it as a what? As a log. Everybody rewrite that as a log. Log what of what equals what? Try it. And then across from you, there's a person directly across from you who you are going to compare with. In your row, it's kind of diagonal-ish between these two rows. Please compare with the people across from you. These two rows, again, slight diagonal, but just a slight diagonal. Compare with the people. If you don't know how to do it, tell them I don't know, and they can maybe show you. I'll pause while you try that. On this one, I'm hoping you said log base 5 of 8, notice I have to jump back and forth, equals x. There you go. Now, does that tell you the answer? No, I haven't told you how to put this in the calculator yet. I haven't, oh, sorry, x equals x, thank you. I haven't told you how to put this in the calculator yet. Again, I think I'm going to take that risk right now and tell you how to put this in the calculator. You would type in log 8 and then end the parentheses because your calculator pops up this, and then you end the parentheses to finish that. Then you say divide by log 5. I just want you to know that it can be done on the calculator. Now, why do you have to type it in that way? Well, basically because they didn't have a good way to have the operating system work to have you type it in directly. You know why? Because in the real world, almost always the base is 10. So if you want to have a different base, like a base of 5, then it's clunky. But if you want to have a base of 10, it works really well. Let me show you what I mean. Log base 10 of 3 equals x. Let's say we're going to type that in. You don't have to type in log 3 divided by log 10. You just type in log 3. Now why? Because log of 10 is equal to 1. All right, that may have just made some heads explode, but if you want to type these in, they can be typed in, and you don't need to know that yet. You don't need to know how to do that, so let's not stress about that. Okay, let's move on to the green one here. The key to logs, to be able to write an equation with exponents in either form and decide which is more useful. I agree with this statement 100%. If you can go back and forth between a log and an exponent and like look at them and say which one is better, then you've got logs almost done, even though we're spending all the way from now to spring break on these things. It almost always comes back to, can you rewrite a log as an exponent, and can you rewrite an exponent as a log? So here's a log problem. Can you rewrite it as an exponent? It's not this. This is a different problem. Can you rewrite this as an exponent problem? Something to the something equals something. Did you say 2 to the 5th equals x? So then you know what the answer is, because you know what 2 to the 5th is. What's 2 to the 5th? 32, so x is 32. Do you get that you just figured out a log problem? You did. Because you could change the log to an exponent, and you know how to do exponents. Okay, now let's go over to the exponent problem and rewrite it as a log. Well, obviously we write the word log. And then what's the first thing you come to? The little base. It's a lower down, it's called a subscript number. And the base is what? 4, log base 4. And then you got to jump to the other side. So what do we say next? Of 12 is x. Now, why is this good? Because x is alone. That's why it's better. And could you find this on a chart somewhere, or on a slide rule, or on your calculator, or on Google? Yes. Okay? So if you can get it so x is alone, that's the main thing. See, x is alone here. So by rewriting it from the one form to the other, if you get the x alone, you pretty much got it solved. Sometimes you need a little help from a calculator to do it. I can't even do that one in my head. These a lot of times come out to weird things like that one we had was 2.807, did you say? 2.807. I'm never going to have that memorized, right? Okay, so let's do some log problems in your head. How could you do a log problem in your head? By throwing in an x, because then it'll make it like all the other ones, and then rewriting it as an exponent problem, which you then will know how to solve. So put an equals x on all of these guys, and then rewrite them all as exponents, and then I guarantee you, you would be able to solve at least 5 out of 6 of these. I know some of you might get stumped on one of them, but otherwise you should be able to do at least 5 out of the 6 of them. I'm going to pause for a second while you give those a shot. Okay, so let's see if you figured these out. This was 3 to the x equals 81. You might be thinking to yourself, I'm supposed to have that memorized? Well, it's just the next logical one. If you did 3 to the 3rd power, that would be 27. So take a wild guess. 3 to the what? 4th. X equals 4. Because 3 to the 4th would be 81. Why? Because it's 3 times 3 times 3 times 3. That's 9. That's 9. 9 times 9 makes 81, right? There's a couple of proofs. So bottom line is the answer is 4 on this one. Okay? Tell me, Alex, what did you rewrite this as? What to the what equals what? Perfect. 8 to the power of x is 1. And then you just have to think it out. 8 to the what makes it equal 1? 8 to the 0 power. X must equal 0. See, if I put a 0 right here, 8 to the 0 is 1, right? Okay? Miss L, read me what you wrote for this one. What to the what is what? 10 to the x equals 10,000. Very nice. Now, there's a very common misconception here that I understand it. People are thinking, okay, it's already got 1 0. So if I want to make it have 3 more zeros, I got to make it this a 3. But that's wrong. It's not a 3. How many of you knew that and you knew it was something else? Raise your hand if you had something else besides 3. You're right. What is it? To the 4th. 10 to the 4th. X is 4. I can prove it. Let me show you something. Do you remember scientific notation? Would you agree 1 times anything is the same exact thing as it is? So 1 times 10 to the 4th is 10,000, isn't it? Okay, so x must be 4. Okay, now this next one. This one's 5 to the x equals 1 over 25. Oh, scary. I got to make it flip and square. So what does that? -2. Good. X must be -2. That way, 5 to the -2 makes it squared and flipped. X is -2. How about this one? 7 to the x equals square root of 7. It'll be easier if I don't say square root of 7 that way. It'll be easier if I say 7 to the 1/2, because that means square root of 7, doesn't it? And then, look, the bases are the same. Therefore, what's x equal to? 1/2. Okay, the next one. 2 to the x equals -4. 2 to what power makes the answer come out negative? Nothing, and therefore no solution. How many of you knew that? There was no solution. Okay, I bet some of you just thought I can't figure it out. The reason you can't figure it out is because it doesn't exist. Yes? Good question. Could you use imaginary numbers? Yes, but then would you say 2 to the I power? Nope, you wouldn't do that. If you wanted to use imaginaries, it theoretically could be done. Well, how about this? 2 to the 2nd would make it 4, right? So what do you think x should be then? So the x is 2i then, is what you're saying, right? Are you saying x should be 2i? I think you're right. 2 to the 2i power. All right, well, in this unit, we're not going to allow imaginary numbers because with logs, you're not allowed to use any bases or arguments that are negative. Yes? Oh, interesting. All right, so you've actually solved it with the calculator, finding the I answer, and it was what again? Okay, well, that's way above our pay grade here, so we're not going to be worrying about imaginary numbers on this. But thanks for bringing it up. And you're right, because she was able to find it with the calculator, that there is an I answer. All right, if you've understood what we've done so far, you should be able to answer these 4 questions. Almost everybody last hour got 4 out of 4. See how you do. You need to complete this quickly, in like 2 minutes. Your homework for tonight, I would consider an easy assignment, really. But since we have almost no time to work because we handed back tests at the beginning of the hour, you're going to have a shortened assignment. What I decided to do is shorten it by cutting out letters C, D, E, and F on all of the problems that have multiple parts, which is only 2 of them. You can skip C, D, E, F. C, Def. Get it? C, D, E, and F. You can skip the C, Def problems. Why did I become a teacher? Okay. Where did that come from? I'm curious. How did the chain of... Oh, okay. All right. I'm glad that was the context. I thought it was like, you shouldn't be a teacher. You're driving me insane, and therefore, why did you become a teacher? All right, anyway. I need to answer these quick because the hour is coming to an end. I hope you knew which one the argument was. Remember how that's the base? That S, that one's the argument. Easy to forget that. We could argue about why it's the argument. Remember that? And then this last one is the exponent. The number at the end is the exponent. A logarithm is an exponent because see how it equals the exponent? It's an exponent. A logarithm is an exponent. Convert that into exponential form. We did a lot of that. 5 to the, wait a minute, there's no letter. You can always say equals x, and you need to know that on your homework too. If there's no x, if it just has a log and it doesn't say equals x, you can say equals x, because then you can go 5 to the x equals 8. Remember how you got to jump around like that? 5 to the x equals 8. That's like this one. And then the last one, remember, since there's no x, I'm going to say equals x and go 1/4 to the x equals 16. And that becomes a problem just like right off our last test where you'd find common bases. You end up saying, okay, I need to take that 1/4 and square it and flip it. And that's the C here. That's squaring it and flipping it. So it was C, C, A, and C. Once again, proving that teachers like the C option the best. Okay, so our homework for tonight. It's fairly shortish. It's not that bad in the first place. It really isn't that bad. As long as you know which one of these is called the argument, which some of you didn't know. This one's the argument. There's a lot of just still terminology questions, and you may skip letters C, D, E, and F wherever they appear. And that's all I got for you for today, and thus for the weekend. All right, take care.